Hello, and welcome to the Science for Sleepy Minds channel. Tonight, we drift into blue. Not the blue of sky or sapphire, but the deeper blue of water, the color that covers 71% of our planet's surface, holds 97% of Earth's water, and cradles life in forms beyond counting. Tonight, we journey into the ocean. We will explore depths that no light has ever touched, meet creatures stranger than dreams, and discover that the ocean is not silent, but singing, a symphony billions of years in the making. So settle now. Let your breathing slow. If you enjoy these peaceful journeys into science and sleep, please like, subscribe, and share. It helps others find their way to rest. Now, close your eyes if you wish. The ocean is waiting. Let us begin. Chapter 1: The Blue Heart of Earth. The ocean is not a place. It is a presence. It covers 362 million square kilometers, an expanse so vast that you could fit 14 billion football fields across its surface, and still have room for more. The ocean covers 71% of Earth's surface, making our planet appear blue from space. From orbit, Earth glows with the soft light of reflected sun on water. Astronauts report that the first thing they see is not land, but blue. Endless, luminous blue stretching across the curved horizon. If Earth were perfectly smooth, ocean water would cover the entire planet to a depth of 2,700 meters, 8,858 feet. Imagine that. No mountains, no continents, only water, wrapping the world like a blanket nearly 3 kilometers deep. The total volume of ocean water is approximately 1.335 billion cubic kilometers. To picture this, if you could gather all that water into a single cube, each side would measure 1,101 kilometers, longer than the distance from New York to Miami. This represents 97% of all water on Earth. The remaining 3% exists as freshwater, locked in ice, flowing in rivers, resting in lakes, or hidden underground. But the ocean holds nearly everything. The average depth of the world's oceans is 3,688 meters, 12,100 feet. More than 2 miles down, on average. Deeper than 10 Empire State Buildings stacked atop one another. Yet this average conceals extremes. Some ocean floors lie shallow, brushed by sunlight. Others plunge into abysses where pressure could crush steel. The deepest point in the ocean is the Mariana Trench, reaching 10,994 meters, 36,070 feet, below sea level. If you placed Mount Everest, the tallest mountain on Earth, into the Mariana Trench, its peak would still rest more than 2 kilometers beneath the surface. Less than 5% of the ocean has been explored by humans. We have mapped the surface of the Moon and Mars in greater detail than our own seafloor. The ocean remains Earth's last great frontier, familiar, yet profoundly unknown. The Pacific Ocean alone contains more water than all of Earth's landmasses combined. It holds 50% of the world's ocean water, stretching across 165 million square kilometers, an area larger than all continents and islands together. If you were to drain the oceans completely, the seafloor would reveal mountains taller than any on land. The Mid-Atlantic Ridge, an underwater mountain range, stretches for 16,000 kilometers, 4 times longer than the Andes, Rockies, and Himalayas combined. The ocean holds approximately 20 million tons of dissolved gold. It is diluted, only about 13 billionths of a gram per liter, but across such vast volume, the total amount equals roughly 20 million tons. Worth trillions, yet forever out of reach. Ocean water contains traces of every naturally occurring element on Earth. Hydrogen and oxygen, yes, but also sodium, magnesium, calcium, potassium, and even uranium, silver, and gold. The ocean is a liquid periodic table, holding 47 million billion tons of dissolved minerals. The weight of all ocean water is approximately 1.4 billion kilograms. A number so large it loses meaning, except to say that the ocean is heavy, pressing down on the planet with the weight of existence itself. The ocean's surface area is greater than the total land area of all continents by 2.5 times. If humans lived evenly distributed across Earth's surface, 7 out of every 10 people would be standing in water. The world's oceans contain more than 230,000 known species, but scientists estimate the true number may exceed 2 million. For every creature we have named, perhaps 10 others swim unnamed, uncounted, unseen. If you removed all life from the ocean, it would still weigh 1.35 billion cubic kilometers of pure water. Life, all the whales, fish, plankton, and coral, represents only a tiny fraction of the ocean's mass. The ocean is mostly emptiness, space, and silence. Yet within that silence, wonders swim. The ocean breathes in ways we are only beginning to understand. It absorbs heat from the sun, distributes warmth across the planet, and moderates climate. It stores carbon, produces oxygen, and sustains life, both in its depths and far beyond its shores. From space, Earth is a blue marble. From the shore, the ocean is horizon. From within, it is universe. Divers speak of weightlessness, of drifting through liquid sky, of the strange peace that comes when surrounded by blue in every direction, above, below, and all around. The ocean is ancient. The ocean is alive. The ocean is patient. It has been here longer than forests, longer than mountains, longer than nearly anything else on this planet. It will be here long after we are gone. Chapter 2: Ancient Waters. The water you touch today is older than the stones beneath your feet. It has been here since the world was young, cycling, circling, always moving, yet never truly leaving. The ocean is approximately 4 billion years old, forming shortly after Earth itself coalesced 4.5 billion years ago. In the beginning, Earth was molten, a churning sphere of liquid rock, bombarded by asteroids and comets. But, hidden within that violence, water was already arriving. Much of Earth's water came from comets and asteroids that struck the planet during its first 500 million years. Each impact delivered ice, frozen water from the outer solar system. Over millions of years, billions of collisions built Earth's oceans drop by drop. Some scientists estimate that volcanic outgassing contributed 50% or more of Earth's water, releasing steam from the planet's interior. Volcanoes exhaled. water vapor rose, cooled, and fell as rain. For millions of years, it rained, a global storm that never stopped, filling basins, carving valleys, creating the first seas. The oldest known water on Earth, found in a Canadian mine, is 2 billion years old, trapped in rock since long before complex life existed. It tastes, scientists say, extremely salty and slightly metallic. It has not seen sunlight in 2,000 million years. In the ocean's earliest days, water temperatures may have exceeded 70 degrees Celsius (158 degrees Fahrenheit), too hot for most life, as we know it today. Yet even in that heat, life began. The first life on Earth appeared in the ocean approximately 3.8 billion years ago. Simple, single-celled organisms that forever changed the planet. They fed on chemicals dissolved in water. They absorbed energy from the sun. And slowly, so slowly, they began releasing oxygen. For the first 2 billion years of ocean life, there was almost no oxygen in the water or air. Earth's atmosphere was thick with methane and carbon dioxide. The ocean was green and rust-colored, stained by dissolved iron. But cyanobacteria, the first photosynthetic organisms, began exhaling oxygen as waste. Around 2.4 billion years ago, oxygen levels rose dramatically in an event called the Great Oxidation Event, rusting iron in the oceans and turning them blue. The world transformed. Ocean water, once murky with iron, became clear. The sky, once orange, became blue. And life, fragile, inventive life, adapted. During the Cryogenian period, between 720 and 635 million years ago, Earth experienced snowball Earth events, where ice may have covered the entire ocean. Temperatures plunged. Ice spread from the poles, creeping across the water until even the equator froze. Life retreated to thermal vents and tiny pockets of liquid water, waiting. When the ice melted, life exploded in diversity during the Cambrian explosion around 541 million years ago. Within 20 million years, the ocean filled with new forms, trilobites, jellyfish, early fish, and creatures so strange we still struggle to classify them. The age of complex ocean life had begun. The ocean has not always been where it is today. Tectonic plates have shifted continents, opened and closed ocean basins dozens of times over Earth's history. 250 million years ago, all continents were joined into a single landmass called Pangaea, surrounded by one vast ocean called Panthalassa, the Universal Sea. The Atlantic Ocean is one of the youngest oceans, beginning to form only 200 million years ago as Pangaea split apart. It is still growing. Every year, the Atlantic widens by about 2.5 centimeters, roughly the speed at which your fingernails grow. The Pacific Ocean, by contrast, is ancient, remnants of Panthalassa, older than any continent. It has been shrinking for 200 million years as tectonic plates shift, yet it remains the largest ocean by far. Around 66 million years ago, an asteroid struck Earth near the Yucatan Peninsula, creating a massive tsunami that swept across ancient oceans. Waves 1,500 meters, nearly a mile, high raced across the water. Coastal ecosystems were scoured clean. The impact triggered mass extinction, ending the age of dinosaurs, but the ocean endured. The water cycle has moved the same water molecules through oceans, clouds, rain, rivers, and back to sea countless times over billions of years. A single water molecule you drink today may once have been part of a prehistoric ocean, swallowed by a dinosaur, frozen in a glacier, or evaporated from a tropical sea 100 million years ago. The ocean holds memory in its chemistry. Layers of sediment on the seafloor preserve hundreds of millions of years of Earth's climate history. Dust from ancient deserts, ash from volcanoes, shells of creatures long extinct. Scientists drill cores from the ocean floor that reveal ice ages, warm periods, asteroid impacts, and the slow drift of continents, all written in mud. The ocean's temperature has varied wildly over geological time. During the Paleocene-Eocene thermal maximum, about 56 million years ago, ocean temperatures rose by 9 to 14 degrees Fahrenheit globally, and even Arctic waters became subtropical. Palm trees grew near the North Pole. Crocodiles swam in Arctic seas. The ocean was a bath, not a chill. Conversely, during ice ages, sea levels dropped by 400 feet or more, as water locked into glaciers. The Atlantic coastline extended hundreds of kilometers farther out. You could walk from Asia to North America across a land bridge that is now beneath the Bering Strait. Entire civilizations may have existed on lands now drowned. The ocean has witnessed every extinction event in Earth's history. 5 mass extinctions reshaped life on this planet, each one leaving the ocean barren and silent before life slowly, patiently, returned. The most severe, the Permian-Triassic extinction 252 million years ago, killed 96% of all marine species. Yet life returned. It always returns. Today's ocean is the product of 4 billion years of patient accumulation, water delivered by space, exhaled by rock, cycled endlessly between sea and sky. It is older than mountains, older than the air we breathe, older than nearly everything we see. The ocean remembers. The ocean endures. The ocean, in its quiet way, is eternal. Chapter 3: The 5 Great Oceans. The ocean is one, a single, interconnected body of water that wraps the planet without border or seam. Yet for human convenience, we have divided it into 5 named regions, each with its own character, its own rhythm, its own story. The Pacific Ocean is the eldest and largest. It covers 165 million square kilometers, more than all the land on Earth combined. It holds 50% of the world's ocean water. It stretches from the Arctic to the Antarctic, from Asia to the Americas, a vast, blue emptiness larger than imagination. The Pacific is so wide that if you flew from one side to the other, you would cross 19,000 kilometers of open water, roughly half the circumference of Earth. Its name means peaceful, given by explorer Ferdinand Magellan, who crossed it during a period of calm winds. But the Pacific is not always peaceful. It births the strongest storms on Earth, typhoons that spin with winds exceeding 300 kilometers per hour. The Pacific Ocean contains more than 25,000 islands, more than all other oceans combined. Some are volcanic peaks, rising sharply from abyssal plains. Others are coral atolls, circular reefs surrounding turquoise lagoons. Many are uninhabited, visited only by seabirds and the slow rhythm of tides. The deepest point on Earth lies here, the Challenger Deep in the Mariana Trench, plunging 36,070 feet below the surface. Only 4 people have ever descended to its bottom. More people have walked on the moon. The Pacific's temperature ranges from freezing near the poles to warm 86 degrees Fahrenheit in tropical regions. Its currents regulate global climate, carrying warm water north and cold water south in a slow, planetary heartbeat. The Atlantic Ocean is younger, narrower, and busier. It formed 200 million years ago as continents split apart, and it is still growing, widening by 2.5 centimeters each year as tectonic plates drift. The Atlantic covers 106 million square kilometers, making it the second largest ocean. It connects the Arctic and Antarctic, separating the Americas from Europe and Africa. For centuries, it was the highway of human exploration, crossed by Vikings, Columbus, and countless ships carrying people, goods, and ideas between continents. The Atlantic is home to the Mid-Atlantic Ridge, the longest mountain range on Earth. It stretches 16,000 kilometers from Iceland to near Antarctica, most of it hidden beneath 8,200 feet of water. At its crest, magma rises from Earth's mantle, creating new seafloor in a process called seafloor spreading. The Atlantic is also home to the Sargasso Sea, a region in the North Atlantic with no land boundaries, defined only by circulating currents. It is calm, clear, and filled with floating sargassum seaweed that forms vast golden mats on the surface. European eels travel thousands of kilometers to spawn here before their young drift back across the ocean. The Atlantic's currents shape climate across 2 continents. The Gulf Stream carries warm water from the Caribbean north along the U.S. East Coast and across to Europe, keeping winters mild in places that would otherwise freeze. Without the Gulf Stream, London would have the climate of Labrador. The Indian Ocean is the warmest of all oceans. It covers 70 million square kilometers, nestled between Africa, Asia, Australia, and Antarctica. Its average surface temperature is 72 degrees Fahrenheit, warm enough to support the richest coral reefs on Earth. The Indian Ocean is defined by monsoons, seasonal wind patterns that reverse direction twice a year, bringing torrential rains to South Asia. For millennia, sailors timed their voyages by these winds, knowing that the monsoon would carry them east in summer and west in winter. The Indian Ocean contains some of the busiest shipping lanes on Earth. 1/3 of the world's bulk cargo passes through its waters, and 2/3 of global oil shipments travel through the Strait of Hormuz, a narrow passage between Oman and Iran. Beneath the surface lie treasures both ancient and geological. The Indian Ocean floor holds evidence of Gondwana, the ancient supercontinent that once joined India, Africa, Australia, and Antarctica. Fragments of that lost world remain in underwater plateaus and ridges. The ocean's islands are equally ancient. Madagascar, Sri Lanka, and the Seychelles are remnants of continental crust, isolated when the ocean formed. The Southern Ocean, also called the Antarctic Ocean, circles the frozen continent at the bottom of the world. It was officially recognized as the fifth ocean in 2000, though mariners have known it for centuries. It covers 20 million square kilometers and is defined by the Antarctic Circumpolar Current, the strongest ocean current on Earth. This current flows eastward, driven by relentless westerly winds, moving 130 million cubic meters of water per second, 600 times the flow of the Amazon River. The Southern Ocean is cold. Surface temperatures rarely rise above 36 degrees Fahrenheit, and in winter, sea ice expands to cover 18 million square kilometers. Yet despite the cold, life thrives. The Southern Ocean produces vast blooms of phytoplankton each spring, feeding krill, tiny shrimp-like creatures that swarm in numbers exceeding 500 trillion individuals. These krill support whales, seals, penguins, and seabirds, making the Southern Ocean one of the most productive ecosystems on Earth. The Arctic Ocean is the smallest and shallowest ocean. It covers 14 million square kilometers, roughly 10 times the size of the Mediterranean Sea. Its average depth is 3,953 feet, shallow compared to others. The Arctic Ocean is almost entirely surrounded by land. North America, Europe, and Asia encircle it, leaving only narrow passages to the Atlantic and Pacific. For most of the year, it is covered by sea ice, frozen ocean water that drifts, cracks, and shifts with currents and wind. In winter, ice covers 15 million square kilometers, an area larger than Antarctica's land surface. In summer, it shrinks to about 7 million square kilometers, though climate change is rapidly reducing this ice. The Arctic Ocean is darkest in winter. From November to February, the sun never rises above the horizon, and the ice glows faintly beneath the stars. In summer, the opposite occurs, 24 hours of daylight for weeks, and the ice takes on shades of turquoise and silver. Beneath the ice, life moves slowly. Polar cod swim in near-freezing water. Seals surface through breathing holes. Narwhals, the unicorns of the sea, dive to depths of 4,900 feet searching for fish. The Arctic Ocean holds vast reserves of oil and natural gas beneath its seafloor, as well as deposits of rare minerals, resources now becoming accessible as ice melts. But extraction comes with profound risks to one of Earth's most fragile environments. Each ocean has its own personality, its own temperature, chemistry, currents, and life. Yet they are not separate. Water flows between them in a continuous, planetary circulation. A drop of water leaving the Pacific may travel through the Indian Ocean, around the tip of Africa, up the Atlantic, into the Arctic, and back. A journey lasting 1,000 years or more. This is called the global ocean conveyor belt, and it connects every sea, every shore, every creature that swims. The 5 oceans are one ocean. The boundaries we draw are illusions. Water knows no borders. The oceans are vast, but they are also one, and in that unity, they sustain everything. Chapter 4: Beneath the Surface. The ocean does not offer itself all at once. It reveals itself in layers, each deeper than the last, each stranger, each more removed from the world of light and air we know. The surface, where waves rise and fall, where sunlight dances, is only the beginning. Beneath lies a vertical world divided into zones, each governed by different rules of pressure, temperature, and light. The sunlight zone, also called the epipelagic zone, extends from the surface down to 656 feet. This is where 90% of all marine life lives. Sunlight penetrates here, allowing photosynthesis. Phytoplankton, microscopic plants, drift by the trillions, forming the foundation of the ocean's food web. Fish school in glittering masses. Dolphins leap. Seabirds dive. The water here is warm in the tropics, up to 86 degrees Fahrenheit, and cold near the poles, sometimes just above freezing. Visibility can reach 200 feet in clear water, far enough to see coral reefs glowing with color, or the silver flash of a tuna racing past. But light does not last forever. By 33 feet deep, red light has been absorbed by water. Everything appears blue or green. By 164 feet, orange light vanishes. By 328 feet, yellow fades away. And by 200 meters, only the faintest blue remains, a twilight that marks the edge of the sunlight zone. Below lies the twilight zone, or mesopelagic zone, stretching from 200 to 656 to 3,280 feet deep. Here, light is dim, too weak for photosynthesis, but enough for eyes to see. This is the realm of bioluminescence, creatures that make their own light. Fish flash blue-green signals to attract mates or lure prey. Jellyfish pulse with ghostly glows. Squid release clouds of luminescent ink to confuse predators. The twilight zone is cold. Temperatures drop to 439 to 50 degrees Fahrenheit, and pressure begins to build. At 1,640 feet, pressure is 50 times greater than at the surface, enough to crush an unprotected human. Yet life thrives here. Lanternfish, small, silvery fish with rows of light-producing organs, migrate upward each night by the billions, rising toward the surface to feed before descending again at dawn. This daily vertical migration is the largest movement of animals on Earth. Scientists estimate that 10 billion tons of creatures rise and fall through the twilight zone every 24 hours, more biomass than all humans combined. Below the twilight zone lies the midnight zone, or bathypelagic zone, from 3,280 to 13,123 feet deep. Here, darkness is absolute. No trace of sunlight reaches this depth. The only light comes from bioluminescent creatures, drifting through the void like stars in an inverted sky. The water is near freezing, 36 to 39 degrees Fahrenheit, and still, currents barely move. Sound travels farther here than anywhere else on Earth, and whales can communicate across thousands of kilometers. Pressure at 2,000 meters is 200 times greater than at the surface, equivalent to having 440 pounds pressing on every square centimeter of your body. At this depth, foam cups sent down in research submersibles shrink to the size of thimbles, compressed by pressure until their air is gone. The creatures here are strange beyond imagining. Anglerfish dangle glowing lures from their heads to attract prey in the dark. Gulper eels have mouths so enormous they can swallow fish larger than themselves. Giant squid drift silently, their eyes, the largest of any animal, 30 centimeters across, designed to catch the faintest glimmer of light. Food is scarce in the midnight zone. Most creatures survive on marine snow, a constant rain of dead plankton, feces, and organic particles drifting down from the surface. It falls slowly, taking weeks to descend through the water column, but it sustains an entire ecosystem hidden in perpetual night. Below 13,123 feet lies the abyssal zone, the deepest layer of the open ocean, extending to 19,685 feet. The abyss is flat, cold, and dark. Pressure here exceeds 600 times surface pressure. Temperatures hover near 36 degrees Fahrenheit. And the seafloor is covered in fine sediment, the remains of billions of years of marine snow. Life here moves slowly. Fish have soft, gelatinous bodies to withstand pressure. Invertebrates crawl across the mud, feeding on organic particles. Everything is adapted for scarcity, slow metabolism, efficient energy use, patience. The abyssal zone covers more than half of Earth's seafloor, the largest habitat on the planet. Yet it remains one of the least explored. Deeper still lies the Hadal Zone, named after Hades, the Greek underworld. This zone includes ocean trenches, the deepest parts of the ocean, from 6,000 to 19,685 to 36,089 feet deep. Only 2% of the ocean floor lies at these depths, yet they represent some of the most extreme environments on Earth. Pressure in the Hadal Zone exceeds 1,000 times surface pressure, 110 megapascals, or 16,000 pounds per square inch. At these pressures, water itself behaves differently. Its density increases, and it can no longer freeze at normal temperatures. Yet life endures even here. Snailfish, translucent and delicate, have been filmed at depths of 26,247 feet. Amphipods, tiny crustaceans, scavenge the seafloor at 32,808 feet. And bacteria thrive in sediment even at the very bottom of the Mariana Trench. The Hadal Zone is not lifeless. It is proof that life finds a way, even in conditions we once thought impossible. Temperature in the ocean varies not just with depth, but with location. Surface temperatures range from 28 degrees Fahrenheit near the poles to 86 degrees Fahrenheit in tropical regions. But below 1,000 meters, temperature becomes almost uniform, hovering around 236 to 39 degrees Fahrenheit across the entire globe. This deep layer of cold water acts as a thermal reservoir, absorbing heat from the surface and slowing climate change. Light, pressure, and temperature together create distinct layers, a vertical architecture that defines where creatures can live, how they move, and what strategies they use to survive. The ocean is not a single environment. It is a stack of worlds, each more alien than the last. And tonight, as you rest, imagine descending slowly through those layers, from sunlight into twilight, from twilight into darkness, from darkness into cold so profound that time itself seems to stop. The surface is where we live, but the depths are where the ocean truly begins. Chapter 5: The Deep Abyss. There are places on Earth deeper than mountains are tall. Places where the ocean floor splits open and plunges into chasms so profound that light, sound, and warmth vanish entirely. These are the ocean trenches, the deepest scars on the planet. More than 20 major trenches cut through the ocean floor, most of them encircling the Pacific Ocean in a region known as the Ring of Fire. The Mariana Trench is the deepest of all. It lies in the western Pacific Ocean, east of the Mariana Islands, and stretches for 1,580 miles, longer than the distance from New York to Denver. At its deepest point, the Challenger Deep, the seafloor plunges 36,070 feet below sea level. To put this in perspective, if you dropped Mount Everest, the tallest mountain on Earth, standing 29,032 feet high, into the Challenger Deep, its peak would still rest 7,038 feet beneath the waves. The Mariana Trench is deeper than commercial airplanes fly high. Pressure at the bottom is 1,086 times greater than at sea level, approximately 110 megapascals, or 16,000 pounds per square inch. This is the equivalent of 50 jumbo jets stacked on top of a single person. At this pressure, air-filled spaces collapse instantly. Bones splinter. Flesh compresses. Yet life exists even here. In 1960, two men, Jacques Picard and Don Walsh, descended to the Challenger Deep aboard the Bathyscaphe Trieste, a deep-sea submersible. They spent 20 minutes on the seafloor, peering through a tiny porthole into the abyss. And they saw life, a flatfish, gliding past, and shrimp-like creatures, moving slowly through the sediment. It was proof that even the deepest place on Earth is not lifeless. In 2012, filmmaker James Cameron became the third person to reach the Challenger Deep, descending solo in the submersible Deep-Sea Challenger. He described the bottom as lunar, a barren, featureless plain covered in fine, pale sediment. No plants, no coral, only darkness, cold, and silence. But the sediment is not empty. Bacteria thrive in the mud, breaking down organic material that drifts down from far above. Amphipods, tiny crustaceans about 1.2 inches long, scavenge the seafloor, feeding on whatever falls from the world above. In 2019, scientists discovered a plastic bag and candy wrappers at the bottom of the Mariana Trench, proof that human pollution has reached even the most remote place on Earth. The Tonga Trench in the South Pacific reaches depths of 35,702 feet, nearly as deep as the Mariana. The Philippine Trench plunges 34,580 feet. The Kuril-Kamchatka Trench reaches 34,587 feet. The Kermadec Trench descends 32,963 feet. Each trench is a unique environment, isolated by depth, geography, and pressure, yet all share similar characteristics. They are cold. Temperatures near the bottom hover just above freezing, around 134 to 39 degrees Fahrenheit. They are dark. No light penetrates beyond 3,280 feet, and the trenches begin far deeper than that. And they are formed by subduction zones, places where one tectonic plate slides beneath another, bending the seafloor downward into deep furrows. As plates collide, the seafloor is pulled down, creating trenches that can be hundreds of kilometers long and tens of kilometers wide. Subduction is slow, only a few centimeters per year, but over millions of years, it shapes the ocean floor like a potter shapes clay. Trenches are not empty voids. They are habitats. Scientists have discovered more than 200 species unique to hadal zones, creatures found nowhere else on Earth. Snailfish are among the deepest living fish ever found. They have soft, translucent bodies with no swim bladders, organs that would collapse under extreme pressure. Their bones are flexible, and their cells are filled with special molecules that stabilize proteins under pressure. One species, Pseudoliparus swirei, was filmed at 26,831 feet in the Mariana Trench, deeper than any other fish recorded. They move slowly through the dark, feeding on small crustaceans and organic debris. Amphipods, by contrast, thrive at even greater depths. In 2019, scientists collected amphipods from 35,853 feet in the Mariana Trench, just 217 feet from the deepest point ever measured. These tiny creatures have adapted to pressure that would obliterate most life. Their cells contain special lipids and proteins that remain stable under extreme conditions. They feed on detritus, breaking down organic material, and recycling nutrients in the deep. Sea cucumbers, soft-bodied invertebrates, crawl slowly across the trench floor, ingesting sediment and extracting nutrients. Some species are translucent, their internal organs visible through their skin. Jellyfish drift through the water column, their bodies pulsing gently. Some species of jellyfish can survive at depths exceeding 32,808 feet, their gelatinous bodies unaffected by pressure. Even microbes thrive here. Bacteria in trench sediments break down organic material, releasing nutrients back into the ecosystem. Some bacteria are piezophils, pressure-loving organisms that cannot survive at surface pressures. They require the crushing weight of the deep to function properly. Trenches are also windows into Earth's interior. At subduction zones, seawater seeps into cracks in the oceanic crust and is pulled down with the descending plate. This water eventually reaches the mantle, where it lowers the melting point of rock and triggers volcanic activity. The result is a chain of volcanoes along the edge of the overriding plate, the Ring of Fire, home to 75% of Earth's active volcanoes. The deepest ocean trenches are geologically active, prone to powerful earthquakes. The 2011 Tohoku earthquake in Japan, magnitude 9.1, occurred at a subduction zone where the Pacific Plate slides beneath the North American Plate. The quake triggered a massive tsunami that devastated Japan's coastline and caused the Fukushima nuclear disaster. Trenches are not static. They shift, deepen, and reshape the ocean floor over millions of years. In some places, sediment from the surface piles up in trenches, slowly filling them. In others, the seafloor continues to sink, carving the abyss ever deeper. Scientists estimate that it would take 20 to 30 million years for marine snow, the organic debris falling from the surface, to completely fill the Mariana Trench. But subduction continues, pulling the floor downward faster than sediment can fill it. Exploring trenches is among the most difficult feats in science. Only 5 descents have been made to the Challenger Deep in history. More than 500 people have been to space. 12 have walked on the moon. But only a handful have touched the deepest point on Earth. The reason is simple. The ocean is hostile. Pressure increases by 1 atmosphere, the pressure at sea level, for every 33 feet of depth. At 10,000 meters, pressure is 1,000 atmospheres, far beyond what any human body can withstand. Submersibles that descend to these depths must be built from titanium or specialized alloys, with walls several inches thick. Even then, the pressure causes the hulls to creak and groan. Every descent is a calculated risk. Yet each expedition reveals new wonders. In 2020, scientists exploring the Mariana Trench discovered 4 new species of amphipods, each uniquely adapted to extreme depth. In 2021, researchers found evidence of active microbial communities living 10,000 meters deep in sediment. Proof that life persists even in the most inhospitable corners of Earth. The trenches remind us that the planet still holds secrets. That despite centuries of exploration, we have only just begun to understand the ocean's depths. And, tonight, as you rest, imagine the abyss, not as emptiness, but as a hidden world. A place where pressure bends reality, where creatures glow in the dark, where the seafloor itself is alive with quiet, persistent life. The trenches are deep, but they are not barren. They are proof that life, once it begins, does not easily surrender. Chapter 6: Currents and Circulation. The ocean is never still. Beneath its surface, water moves in vast rivers, currents that flow thousands of kilometers, carrying warmth from the equator to the poles, cold from the poles to the tropics, and life from shore to shore. These currents are the ocean's circulatory system, invisible highways that shape climate, weather, and the distribution of marine life across the planet. The Gulf Stream is one of the most powerful ocean currents on Earth. It carries warm water from the Caribbean north along the eastern coast of the United States, then crosses the Atlantic toward Europe. The Gulf Stream moves at speeds up to 5.6 miles per hour, faster than most people walk. It transports approximately 100 million cubic meters of water per second, 100 times the combined flow of all rivers on Earth. This immense flow of warm water keeps Western Europe's climate mild. Without the Gulf Stream, London would have winters as cold as Labrador, Canada, which sits at the same latitude. Paris would freeze. Reykjavik would be uninhabitable. The Gulf Stream is part of a larger system called the North Atlantic Gyre, a massive circular current system that dominates the North Atlantic Ocean. Gyres are formed by the Coriolis effect, the rotation of the Earth, which deflects, moving water to the right in the northern hemisphere and to the left in the southern hemisphere. There are 5 major ocean gyres: the North Atlantic, South Atlantic, North Pacific, South Pacific, and Indian Ocean gyres. Each gyre circulates slowly, completing one full rotation every several years. The center of a gyre is often calm, a region where water accumulates, along with floating debris. The Great Pacific Garbage Patch, a massive accumulation of plastic waste, sits in the center of the North Pacific Gyre, covering an area twice the size of Texas. Deep beneath the surface currents lies another system, the thermohaline circulation, also known as the global ocean conveyor belt. This circulation is driven not by wind, but by differences in temperature, thermo, and salinity, haline. Cold, salty water is denser than warm, fresh water. When seawater near the poles cools and ice forms, the remaining water becomes saltier and denser. This dense water sinks to the ocean floor and flows toward the equator in slow, deep currents. In the North Atlantic, near Greenland and Iceland, surface water cools and sinks, beginning a journey that will carry it around the world. This sinking water flows south along the ocean floor, crosses the equator, and enters the Southern Ocean, where it joins the Antarctic Circumpolar Current, the world's strongest current. The Antarctic Circumpolar Current flows eastward around Antarctica, driven by powerful westerly winds. It moves 130 million cubic meters of water per second, more than any other current. From the Southern Ocean, deep water flows north into the Indian and Pacific Oceans, slowly rising toward the surface over hundreds of years. Eventually, this water warms, returns to the surface, and flows back toward the Atlantic, completing the loop. The entire journey, from sinking in the North Atlantic to rising in the Pacific and returning, takes approximately 1,000 years. This circulation redistributes heat around the planet. Without it, the tropics would be unbearably hot, and the poles even colder than they are now. It also carries oxygen and nutrients to the deep ocean, sustaining life in the abyss. Ocean currents are influenced by wind patterns, particularly the trade winds and westerlies. The trade winds blow from east to west near the equator, pushing surface water westward and creating the equatorial currents. When this water piles up against continents, it has nowhere to go but north or south, forming currents like the Gulf Stream and the Kuroshio Current in the Pacific. The westerlies, winds that blow from west to east in mid-latitudes, drive currents like the North Atlantic Drift and the West Wind Drift in the Southern Ocean. Currents also shape the distribution of marine life. Nutrient-rich water from the deep ocean rises to the surface in a process called upwelling, often along coastlines where winds push surface water away from shore. The Humboldt Current, which flows north along the coast of South America, is one of the most productive upwelling zones on Earth. Cold water, rising from the deep, brings nutrients to the surface, feeding vast blooms of phytoplankton. These microscopic plants support anchovies, which in turn feed seabirds, sea lions, and whales. The Humboldt Current supports 20% of the world's fish catch, despite covering less than 0.1% of the ocean's surface. El Niño and La Niña are disruptions to normal ocean currents in the Pacific. During El Niño, warm water that normally pools in the western Pacific shifts eastward towards South America. This disrupts upwelling, reducing fish populations and altering weather patterns worldwide, causing droughts in some regions and floods in others. El Niño events occur every 2 to 7 years and can last 9 to 12 months. La Niña is the opposite, cooler than normal water in the eastern Pacific, which strengthens upwelling and intensifies normal weather patterns. Ocean currents also carry heat-loving species to unexpected places. Sea turtles that hatch on beaches in Japan can ride the Kuroshio Current across the Pacific to California, traveling 6,200 miles in just a few years. European eels spawn in the Sargasso Sea, then their larvae drift on currents for 1 to 3 years, eventually reaching rivers in Europe where they mature. Even plastic waste travels the world on ocean currents. A rubber duck lost overboard in the Pacific in 1992 washed ashore in Scotland 11 years later, having circled the globe on the North Pacific and Atlantic gyres. Currents near the seafloor move much more slowly than surface currents. Deep ocean water creeps along at speeds of just a few millimeters per second, so slow that it can take centuries for water to move from one ocean basin to another. Yet, even this sluggish flow is vital. It delivers oxygen to deep-sea creatures and recycles nutrients across the planet. Some currents are seasonal. The monsoon currents in the Indian Ocean reverse direction twice a year, driven by shifting wind patterns over South Asia. In summer, winds blow from the southwest, creating currents that flow northeast. In winter, winds reverse, and so do the currents. For thousands of years, sailors used these predictable shifts to navigate between Africa, India, and Southeast Asia. Ocean currents influence not just climate, but also history. The Gulf Stream helped Christopher Columbus cross the Atlantic by carrying him back to Europe after reaching the Caribbean. The California Current, flowing south along the U.S. West Coast, carried Spanish explorers north from Mexico. And the Kuroshio Current helped ancient Polynesians navigate across the Pacific, reaching islands thousands of kilometers from their homelands. Currents are the ocean's veins, carrying warmth, nutrients, oxygen, and life. They connect distant shores, link ecosystems, and regulate the planet's climate. Without currents, the ocean would stratify, warm water above, cold water below, with little mixing. Life in the deep would suffocate. The poles would freeze solid, and the tropics would boil. But the ocean does not stand still. It flows, circulates, and breathes, a living system in constant motion. Chapter 7: Waves and Tides. The ocean is never flat. Even on the calmest day, water rises and falls, ripples and swells, moved by forces both near and impossibly distant. Waves and tides are the ocean's breath, rhythms that have pulsed since the world began, shaping shores and guiding life. Waves are born from wind. When wind blows across the ocean surface, friction transfers energy from air to water. Small ripples form, then grow into larger waves as the wind continues to push. The size of a wave depends on three things: wind speed, wind duration, and fetch, the distance over which the wind blows uninterrupted. A gentle breeze creates ripples only centimeters high. A storm with winds of 62 miles per hour blowing for 24 hours across 500 kilometers of open ocean can generate waves 33 feet tall. The largest wind-driven waves ever reliably recorded reached heights of 98 feet, taller than a 10-story building. These massive waves, called rogue waves, appear suddenly in open ocean, often without warning. Rogue waves are not just tall, they are steep, with deep troughs and sharp crests. They can snap ships in half, and have been responsible for numerous maritime disasters. For centuries, sailors reported rogue waves, but scientists dismissed them as myth. Then, on January 1, 1995, a wave 85 feet high struck the Dropner oil platform in the North Sea, confirming their existence. Since then, scientists have recorded dozens of rogue waves using satellite data and ocean buoys. Waves travel across oceans in groups called wave trains. Interestingly, Individual waves within a train move faster than the group itself. A wave forms at the back of the group, travels forward through the train, and disappears at the front, only to be replaced by a new wave, forming at the back. The wave pattern moves, but the water itself mostly stays in place, oscillating up and down. When waves approach shallow water near shore, their behavior changes. The wave's base drags against the seafloor, slowing down. But the top of the wave continues, moving at its original speed, causing the wave to steepen and eventually topple forward, creating breakers. The type of breaker depends on the slope of the seafloor. Spilling breakers form on gentle slopes, with foam cascading down the front of the wave. Plunging breakers form on steeper slopes, curling over to create the classic tube that surfers seek. Surging breakers occur on very steep slopes, where waves rise and collapse against the shore without breaking. Not all waves are caused by wind. Tsunamis are waves generated by underwater earthquakes, volcanic eruptions, or landslides. Unlike wind waves, which affect only the surface, tsunamis move the entire water column from surface to seafloor. In deep ocean, tsunamis travel at speeds exceeding 500 miles per hour, as fast as a jet airliner, but their height is only 30 to 60 centimeters, 1 to 2 feet, making them nearly invisible. As a tsunami approaches shallow water, it slows down, but the energy has to go somewhere. The wave compresses, and its height increases dramatically. A tsunami that was barely noticeable in deep water can rise to 10, 20, even 33 to 98 feet when it reaches shore. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake off Sumatra, killed more than 230,000 people across 14 countries. Waves reached heights of 30 meters in some areas, traveling several kilometers inland. The 2011 Tohoku tsunami in Japan reached heights of 131 feet in some locations, as tall as a 13-story building. Tsunamis can cross entire ocean basins. The 2011 tsunami was detected in Antarctica, California, and Chile, places thousands of kilometers from the earthquake's epicenter. While waves are driven by wind and earthquakes, tides are driven by the moon and sun. Tides are the rise and fall of sea level caused by gravitational pull. The moon, being closer to Earth, exerts a stronger pull than the sun. As the moon orbits, its gravity pulls on Earth's oceans, creating a bulge of water on the side of Earth facing the moon. But there's also a bulge on the opposite side. This happens because the moon's gravity pulls more strongly on the near side of Earth than on the far side, stretching the ocean into an ellipse. As Earth rotates through these two bulges, most coastal areas experience 2 high tides and 2 low tides every day, approximately every 12 hours and 25 minutes. The sun also influences tides, though its effect is about half as strong as the moon's. When the sun, moon, and Earth align, during a new moon or full moon, their gravitational forces combine, creating spring tides with the highest highs and lowest lows. When the sun and moon are at right angles, during the first and third quarters, their forces partially cancel out, creating neap tides with smaller differences between high and low water. The range between high and low tide varies dramatically depending on location. In the open ocean, tidal range is typically only 30 to 60 centimeters, 1 to 2 feet. But, in coastal areas, especially those with funnel-shaped bays, tides can be extreme. The Bay of Fundy in Canada has the highest tides in the world. The difference between high and low tide can reach 52 feet, the height of a 5-story building. Twice each day, 160 billion tons of water flow in and out of the bay. At low tide, vast mudflats emerge, exposing the seafloor. At high tide, water floods back in, rising several meters per hour. The Severn Estuary in the United Kingdom experiences tides up to 49 feet. The Bay of Mont-Saint-Michel in France sees tides of 46 feet, said to come in as fast as a galloping horse. In contrast, the Mediterranean Sea, nearly enclosed by land, has almost no tide, with ranges typically less than 30 centimeters, 1 foot. Tides don't just affect water level. They create tidal currents, the horizontal movement of water as tides rise and fall. In narrow channels and straits, tidal currents can be powerful. The Saltstraumen in Norway is the world's strongest tidal current, reaching speeds of 20 knots, 37 kilometers per hour or 23 miles per hour, faster than most boats can travel. Water rushes through a narrow strait between islands, creating whirlpools and eddies that can trap unwary vessels. Tidal currents shape coastal ecosystems. Salt marshes, mangroves, and estuaries are flooded and drained twice daily, creating unique habitats for species adapted to constant change. Fiddler crabs emerge at low tide to feed on the mudflats. Fish swim into marshes at high tide to hunt among the grasses. Shorebirds follow the tides, feeding on exposed invertebrates. Many marine creatures time their reproduction to the tides. Grunion, small fish found in California, spawn only on the highest spring tides, laying eggs in the sand just above the high tide line. The eggs incubate for 2 weeks, safe from predators, until the next spring tide washes them back into the sea. Horseshoe crabs come ashore in massive numbers during spring tides to lay eggs on beaches. Shorebirds time their migrations to coincide with these spawning events, gorging on eggs to fuel their long flights. Even plants respond to tides. Some species of mangrove shed seeds only at high tide, allowing them to float away and colonize new areas. Humans have used tides for millennia. Tidal mills, powered by the flow of water at high tide, have existed for more than 1,000 years, grinding grain and sawing wood. Today, engineers are developing tidal power stations that generate electricity from tidal currents. The La Rance Tidal Power Station in France, built in 1966, generates 240 megawatts of electricity, enough to power 240,000 homes. Scotland's Maygen project, completed in 2017, uses underwater turbines to capture energy from tidal currents in the North Sea. Tidal power is predictable. Unlike wind or solar, tides never stop, never falter, never change unexpectedly. Waves and tides are constants, forces that have shaped the ocean since its beginning. They carve coastlines, transport sediment, mix nutrients, and create habitats. They are the ocean's rhythm, sometimes gentle, sometimes violent, but always present. Chapter 8: The Chemistry of Salt. The ocean tastes of salt. Not sweet, not bitter, just salt. Ancient, mineral, enduring. Every liter of seawater contains approximately 35 grams of dissolved salts, a concentration of 3.5%. This may not sound like much, but across the entire ocean, it adds up to 50 quadrillion tons of dissolved minerals. If you could extract all the salt from the ocean and spread it over the land, it would form a layer 500 feet thick, taller than the Great Pyramid of Giza. The saltiness of seawater is measured in parts per thousand, ppt, also called salinity. Average ocean salinity is 35 ppt, meaning 35 grams of salt per kilogram of water. But salinity varies depending on location. In the Red Sea, where evaporation is high and rainfall low, salinity reaches 41 ppt. In the Baltic Sea, fed by rivers and surrounded by land, salinity drops to 7 to 8 ppt, barely salty at all. Near the mouths of large rivers, freshwater mixes with seawater, creating brackish water with salinity between 0.5 and 30 ppt. Estuaries, where rivers meet the sea, are among the most productive ecosystems on Earth, supporting fish, birds, and countless invertebrates adapted to fluctuating salinity. The primary salt in seawater is sodium chloride, NaCl, table salt, which makes up about 85% of dissolved salts. But ocean water also contains magnesium, calcium, potassium, sulfur, and traces of nearly every element on the periodic table. There is enough gold dissolved in the ocean to give every person on Earth 9 pounds, but it is so diluted, 13 parts per trillion, that extracting it would be impossibly expensive. There is enough uranium in seawater to power the world's nuclear reactors for thousands of years, but again, the concentration is too low for practical extraction. There is even silver, copper, zinc, and iodine, all present in trace amounts, invisible yet real. The ocean's saltiness comes from two main sources, rivers and underwater volcanoes. Rivers carry dissolved minerals eroded from rocks and soil. Over billions of years, these minerals have accumulated in the ocean. When water evaporates from the ocean surface, it leaves the salt behind, concentrating it further. Underwater volcanoes and hydrothermal vents also contribute. Hot water circulating through volcanic rock dissolves minerals and carries them into the ocean. At hydrothermal vents, water heated to 750 degrees Fahrenheit erupts from the seafloor, spewing minerals like iron, zinc, copper, and sulfur. The ocean has been salty for at least 3.5 billion years, possibly longer. Early oceans may have been even saltier than today, or they may have been fresher, with salt accumulating gradually over time. Scientists are still debating, but one thing is certain: the ocean's chemistry has remained remarkably stable for hundreds of millions of years. Salinity affects density. Saltwater is denser than freshwater, which is why it's easier to float in the ocean than in a lake. The Dead Sea, with a salinity of 340 ppt, nearly 10 times saltier than the ocean, is so dense that swimmers float effortlessly on the surface, unable to sink. Cold water is also denser than warm water. The densest water on Earth is cold and salty, found near the poles, where surface water freezes, leaving behind extra salty brine that sinks to the ocean floor. This dense water drives the thermohaline circulation, the global ocean conveyor belt that carries water from the surface to the deep and back again over 1,000-year cycles. The ocean contains more than just salt. It holds dissolved gases, oxygen, carbon dioxide, nitrogen, and others. Oxygen, O2, is essential for marine life. It enters the ocean from the atmosphere and is produced by phytoplankton during photosynthesis. Oxygen concentration decreases with depth. In the sunlight zone, oxygen levels are high, up to 8 milligrams per liter. In the deep ocean, levels drop to 2 to 4 mg/L. In some regions, oxygen disappears entirely, creating oxygen minimum zones, OMZs. Areas where oxygen levels fall below 0.5 milligrams per liter. Most fish cannot survive in OMZs. But some species, like vampire squid and certain jellyfish, have evolved to thrive in low-oxygen environments. Carbon dioxide, CO2, is equally important. The ocean absorbs about 30% of the CO2 released by human activities, approximately 10 billion tons per year. This helps slow global warming, but it comes at a cost. The CO2 reacts with seawater to form carbonic acid, lowering the ocean's pH. Since the Industrial Revolution, ocean pH has dropped from 8.2 to 8.1, a 25% increase in acidity. This process, called ocean acidification, makes it harder for marine organisms to build shells and skeletons from calcium carbonate. Coral, mollusks, sea urchins, and plankton all struggle in more acidic water. If CO2 emissions continue unchecked, ocean pH could drop to 7.8 by 2100, a level not seen in 14 million years. The ocean also contains nutrients, nitrogen, phosphorus, and iron, essential for life. Nitrogen is the most important. It exists in seawater as nitrate, NO3, which phytoplankton use to build proteins. Nitrogen is abundant in the deep ocean, but scarce at the surface, where phytoplankton consume it rapidly. Upwelling, the rise of deep water to the surface, brings nutrients back to the sunlight zone, triggering massive blooms of phytoplankton. These blooms are visible from space, turning entire regions of ocean green. Phosphorus is another limiting nutrient. Without it, phytoplankton cannot grow, even if nitrogen is abundant. Iron is critical in some regions, particularly the Southern Ocean, where iron is so scarce that adding even tiny amounts can trigger massive blooms. In fact, scientists have proposed iron fertilization, dumping iron into the ocean to boost phytoplankton growth and absorb CO2 from the atmosphere. Early experiments worked. Iron triggered blooms. But the long-term effects remain unknown, and many scientists worry about unintended consequences. The ocean's chemistry is a delicate balance. Too much salt, and organisms cannot regulate their internal water. Too little oxygen, and fish suffocate. Too much acid, and shells dissolve. Every element, every molecule, every ion plays a role in the vast, interconnected system we call the sea. Seawater is not just water. It is a solution, a living chemistry set, a mineral broth that has nurtured life for billions of years. The ocean is not just liquid. It is life itself, dissolved. Chapter 9: Colors of the Deep. The ocean is blue. But why? Not because it reflects the sky, though many believe this. Water itself is blue. Pure water absorbs red light more than blue. When sunlight enters the ocean, red wavelengths are absorbed first, followed by orange, yellow, and green. Blue light penetrates deepest, which is why the ocean appears blue. In shallow water, the blue is pale, almost transparent. In deep water, the blue darkens, rich, profound, endless. The color also depends on what lives in the water. In regions rich with phytoplankton, microscopic plants containing chlorophyll, the ocean appears green. Chlorophyll absorbs red and blue light, reflecting green back to our eyes. In areas with massive algal blooms, the ocean turns vivid green, sometimes visible from space. The Sargasso Sea is named for floating sargassum seaweed, which gives the water a golden brown hue. Near river mouths, the ocean appears brown or murky, stained by sediment carried from land. The Yellow Sea, between China and Korea, takes its name from the yellow sediment washed down by the Yellow River. In polar regions, the ocean can appear milky white or pale blue-green, colored by high concentrations of calcium carbonate from coccolithophores, tiny plankton with chalky shells. Some parts of the ocean glow red, not from algae, but from red tides, blooms of toxic dinoflagellates that turn water the color of rust. These blooms can kill fish, poison shellfish, and make beaches hazardous. But the most magical colors in the ocean come not from the water itself, but from the creatures within it. Bioluminescence, the production of light by living organisms, is one of the ocean's most widespread phenomena. Scientists estimate that 76% of ocean animals produce light. In the deep sea, where sunlight never reaches, bioluminescence is the only light that exists. Creatures create light through chemical reactions. A molecule called luciferin reacts with oxygen, catalyzed by the enzyme luciferase, releasing energy as light. The light produced is usually blue or blue-green, the colors that travel farthest in water. But some species produce red or even yellow light, which is invisible to most predators. Anglerfish use bioluminescent lures dangling from their heads to attract prey. In the pitch-black deep, a glowing bait is irresistible until it's too late. Lanternfish have rows of light-producing organs called photophores along their sides. These lights may help them recognize others of their species, or confuse predators by breaking up their silhouette. Firefly squid, found off the coast of Japan, have thousands of tiny photophores covering their bodies. When threatened, they flash brightly, disorienting attackers. During mating season, millions of firefly squid gather near shore, turning the water into a glowing spectacle, one of the ocean's most stunning natural displays. Jellyfish are among the most famous bioluminescent creatures. The crystal jellyfish, Equoria victoria, produces green light from a protein called GFP, green fluorescent protein. Scientists later isolated GFP and used it to tag genes in medical research, a discovery that won the Nobel Prize in Chemistry in 2008. Dinoflagellates, single-celled plankton, create milky seas, a phenomenon where entire stretches of ocean glow faintly at night. When disturbed by waves, boats, or swimming creatures, dinoflagellates emit flashes of blue light. This creates bioluminescent waves, glowing surf that rolls onto beaches, leaving trails of sparkle in the sand. Bioluminescence serves many purposes. Some creatures use it to attract prey. Others use it to lure mates, flashing patterns like underwater Morse code. Some use it for defense, blinding predators with sudden bursts of light, or releasing glowing clouds to create decoys. A few deep-sea creatures use bioluminescence as camouflage. They produce light on their undersides to match the faint glow from above, erasing their shadows and making them invisible to predators below. This is called counterillumination, and it's remarkably effective. Not all ocean colors are visible to human eyes. Ultraviolet, UV, light penetrates water, and some marine animals can see it. Mantis shrimp have the most complex eyes in the animal kingdom. 16 types of photoreceptors compared to our 3. They see colors we cannot imagine, including ultraviolet and polarized light. Their world is a riot of color invisible to us. Even in the darkest depths, where no sunlight reaches, some creatures can see using infrared light. Certain deep-sea fish have evolved to detect heat signatures from other animals, a form of night vision adapted to the abyss. The ocean's colors also change with depth. At 33 feet, red light disappears. Everything looks blue or green. Red fish appear black at this depth, making them nearly invisible. At 164 feet, orange vanishes. At 328 feet, yellow fades. By 656 feet, only blue remains, a dim, twilight blue. Below 3,280 feet, there is no natural light at all. Only the glow of bioluminescent creatures, drifting through the void. Divers who descend beyond the sunlight zone describe it as entering another world, one where color no longer exists, except for the brief, ghostly flashes of life passing by. The ocean's color is not static. It shifts with the sun's angle, the weather, the season, and the life within it. In the tropics, water is so clear it appears almost transparent. You can see 200 feet down to coral reefs glowing in vibrant hues. In colder seas, the water is murky, rich with plankton, and the color is a deep blue-green. After storms, sediment stirs from the bottom, and the ocean turns gray or brown, a temporary cloudiness that clears within days. During red tides, the ocean turns the color of blood, beautiful, but deadly. During plankton blooms, it glows neon green, visible from satellites orbiting 250 miles above. The ocean holds every shade of blue, green, black, and silver. It holds light that shimmers, glows, and fades. It holds colors we can see, and colors we cannot. Chapter 10. Smallest Lives. The ocean teems with life so small it is invisible. You cannot see them with the naked eye. Yet, they outnumber all other life on Earth combined. These are the plankton, drifters, floaters, the foundation of every ocean ecosystem. The word plankton comes from the Greek planktos, meaning wanderer or drifter. Plankton cannot swim against currents. They drift wherever the ocean carries them. There are two main types, phytoplankton and zooplankton. Phytoplankton are microscopic plants, bacteria, algae, and other photosynthetic organisms. Despite their size, phytoplankton produce 50% of Earth's oxygen, more than all forests, grasslands, and jungles combined. Every other breath you take comes from the ocean. There are approximately 100 million phytoplankton in a single liter of seawater. Multiply that across the ocean's 1.335 billion cubic kilometers of water, and the number becomes unfathomable. The most common phytoplankton are diatoms, single-celled algae encased in intricate glass shells made of silica. Under a microscope, diatoms are stunningly beautiful, geometric, symmetrical, delicate as snowflakes. There are more than 100,000 species of diatoms, each with its own unique shape. Some are shaped like stars, others like cylinders, triangles, or discs. No two species are exactly alike. Diatoms are incredibly productive. A single diatom can divide and create 100 million descendants in just 1 month. When conditions are right, plenty of sunlight, nutrients, and calm water, diatoms bloom by the trillions, turning the ocean green and producing vast amounts of oxygen. Cyanobacteria, also called blue-green algae, are among the oldest life forms on Earth. They evolved 3.5 billion years ago and were the first organisms to perform photosynthesis. Prochlorococcus, a type of cyanobacteria, is the smallest photosynthetic organism on Earth, just 0.6 micrometers across. But what it lacks in size, it makes up for in numbers. Octillions of Prochlorococcus cells float in the ocean, so many that they produce 20% of Earth's oxygen despite being individually invisible. Dinoflagellates are another type of phytoplankton, single-celled organisms that can swim using 2 whip-like flagella. Some dinoflagellates are photosynthetic, producing energy from sunlight. Others are predatory, hunting and consuming other plankton. Many dinoflagellates are bioluminescent, flashing blue light when disturbed, creating the glowing waves seen on some beaches at night. But some dinoflagellates are dangerous. Species like Carenia brevis produce toxins that cause red tides, poisoning fish, and making shellfish unsafe to eat. Humans who consume contaminated shellfish can suffer paralytic shellfish poisoning, which can be fatal. While phytoplankton produce energy from sunlight, zooplankton are animals, and they eat. Copepods are the most abundant zooplankton. These tiny crustaceans, usually 1 to 2 millimeters long, look like miniature shrimp. There are more than 13,000 species of copepods, living in every ocean from the surface to the abyss. Scientists estimate there are 1 billion copepods in the ocean, making them one of the most numerous animals on Earth. Copepods feed on phytoplankton, filtering thousands of cells through their bristly limbs each day. In turn, copepods are eaten by fish, whales, seabirds, and countless other predators. They are a critical link in the ocean food web. Without copepods, larger animals would starve. Krill are larger zooplankton, shrimp-like creatures about 2.4 inches long. They swarm in massive numbers, particularly in polar oceans. The Antarctic krill, Euphausia superba, form swarms so dense they can be seen from space, covering thousands of square kilometers. A single swarm can contain 10,000 krill per cubic meter, billions of individuals, moving as one. Krill are the primary food source for baleen whales, seals, penguins, and many fish. A single blue whale can eat 4 tons of krill per day, roughly 40 million individuals. Despite being eaten in such vast quantities, krill populations remain stable, a testament to their rapid reproduction. Female krill can produce 10,000 eggs per spawning, and they spawn multiple times per season. Jellyfish begin life as plankton. After hatching, jellyfish spend their early days as tiny, drifting larvae called planulae, no larger than a grain of sand. They drift with currents, feeding on even smaller plankton, growing slowly until they settle on the seafloor and transform into polyps. Eventually, the polyps release new jellyfish, completing the cycle. Larval fish are also plankton. When fish hatch from eggs, they are tiny, often just 2 to 3 millimeters long, and completely helpless. They drift with currents, feeding on phytoplankton and microzooplankton, trying to survive long enough to grow into juveniles. Mortality is brutal. Out of 10,000 fish eggs, only 1 to 10 may survive to adulthood. The rest are eaten by predators, starve, or drift into unsuitable habitats. Even the eggs of large animals like sea turtles and octopuses begin as plankton, drifting in the open ocean before hatching. Plankton are not just food, they are architects of the ocean. When phytoplankton die, their cells sink slowly through the water, carrying carbon from the surface to the deep ocean. This process, called the biological carbon pump, removes 10 billion tons of carbon from the atmosphere every year, helping to regulate Earth's climate. Some of this carbon is buried in seafloor sediment, where it remains for millions of years, eventually turning into oil and natural gas. The fossil fuels we burn today were once plankton, drifting in ancient seas. Phytoplankton also produce dimethyl sulfide, DMS, a gas that rises into the atmosphere and helps form clouds. More phytoplankton means more DMS, which means more clouds, which reflects sunlight and cools the planet. The ocean and sky are connected through plankton, tiny organisms influencing the weather across the globe. Plankton are so small, yet so vital. They produce oxygen, they feed the ocean, they regulate climate, they sink carbon. Without plankton, the ocean would be a sterile desert. And, without the ocean's plankton, life on land, including us, would not exist. An ocean within the ocean. A world we cannot see, but cannot survive without. Chapter 11. Coral Kingdoms. Beneath warm, shallow waters, cities grow. Not cities of stone and steel, but cities of life, built by creatures smaller than your fingernail, constructed over centuries, hosting thousands of species in structures more intricate than any human architecture. These are coral reefs, the rainforests of the sea. Coral reefs cover less than 0.1% of the ocean floor, yet they support 25% of all marine species. More than 4,000 species of fish live on coral reefs. More than 800 species of coral build them. And countless invertebrates, shrimp, crabs, sea stars, urchins, worms, find shelter in their crevices. A single coral reef can host more than 1,000 species in an area the size of a football field. But coral themselves are not plants. They are animals, tiny polyps related to jellyfish and sea anemones. Each coral polyp is only a few millimeters across, a soft-bodied creature with a mouth surrounded by stinging tentacles. The polyp secretes calcium carbonate beneath itself, building a hard skeleton that becomes the reef's foundation. Over time, hundreds or thousands of years, millions of polyps working together create structures visible from space. The Great Barrier Reef, off the coast of Australia, is the largest living structure on Earth. It stretches for 1,400 miles, longer than the distance from New York to Miami. It covers an area of 133,000 square miles, larger than Italy. It contains 2,900 individual reefs and 900 islands. And it was built entirely by organisms so small you could hold dozens in the palm of your hand. Coral polyps cannot build reefs alone. They have partners, microscopic algae called zooxanthellae that live inside their tissues. These algae perform photosynthesis, using sunlight to produce sugars and oxygen. The coral receives up to 90% of its energy from these algae. In return, the coral provides the algae with shelter, nutrients, and access to sunlight. This partnership, called symbiosis, is the foundation of every coral reef on Earth. But the relationship is fragile. When water becomes too warm, even just 12 to 4 degrees Fahrenheit above normal, coral expel their zooxanthellae in a stress response. Without the algae, coral lose their color, turning ghostly white, a phenomenon called coral bleaching. Bleached coral are not dead, not yet. But without their algae, they begin to starve. If temperatures return to normal within weeks, the zooxanthellae can return, and the coral recovers. But if the heat persists, the coral dies. In 2016, the Great Barrier Reef experienced the worst bleaching event in recorded history. 30% of the reef's coral died. In 2017, bleaching struck again. Another 20% died. In just 2 years, the reef lost half of its coral, structures that had taken centuries to grow. Coral reefs grow slowly. Fast-growing branching corals can add 104 to 8 inches per year. Slow-growing massive corals add only 10.4 to 1.2 inches per year. Some coral colonies are hundreds of years old. The oldest known coral, a massive Porrites coral in the Pacific, is more than 4,000 years old, older than the pyramids of Egypt. Coral reefs form in 3 main types. Fringing reefs grow directly along coastlines, separated from shore by shallow lagoons. Barrier reefs form farther offshore, separated from land by deeper water. Atolls are circular or horseshoe-shaped reefs surrounding lagoons, often with no island in the center. Atolls form when volcanic islands sink slowly into the ocean. The coral continues, growing upward, as the island disappears, eventually leaving only the reef behind. Corals spawn in spectacular mass events, often tied to moon phases and water temperature. Once a year, usually a few nights after a full moon, entire reefs release eggs and sperm simultaneously. Billions of tiny pink, orange, and white bundles float to the surface, creating underwater snowstorms in reverse. This synchronized spawning maximizes the chance that eggs will be fertilized before currents scatter them. Coral larvae drift for days or weeks before settling on hard surfaces and beginning new colonies. Reefs provide vital services to both ocean life and humans. They act as natural breakwaters, absorbing 97% of wave energy and protecting coastlines from storms and erosion. They support fisheries that feed 1 billion people worldwide. They generate $375 billion annually through tourism, fishing, and coastal protection. But reefs are disappearing. 50% of the world's coral reefs have been lost in the past 30 years. Climate change, pollution, overfishing, and coastal development all threaten their survival. If current trends continue, 90% of reefs could be gone by 2050. Yet, reefs are resilient if we give them a chance. Marine protected areas, reduced pollution, and climate action can help reefs recover. Some scientists are experimenting with coral restoration, growing coral in nurseries, and transplanting them to damaged reefs. Others are breeding heat-resistant coral, selecting individuals that survived bleaching events, and propagating their offspring. In the Caribbean, staghorn and elkhorn coral, once dominant species, were listed as threatened in 2006 after losing 95% of their populations. But restoration efforts have brought them back in some areas, with thousands of coral fragments growing into thriving colonies. Coral reefs are among the most vibrant, beautiful, and productive ecosystems on Earth. They are home to clownfish hiding in anemones, parrotfish crunching coral skeletons to create sand, sea turtles gliding over fields of color, and sharks patrolling the edges, where reef meets open ocean. They are nurseries for fish that will journey across oceans. They are fortresses sheltering creatures from predators. They are gardens tended by nature over millennia. And, tonight, as you drift toward sleep, imagine yourself floating above a reef, the water warm and clear, sunlight filtering down in shafts of gold. Below you, coral branches sway gently in the current. Fish dart through shadows. Colors bloom in every direction: purple, yellow, orange, blue. The reef is quiet, but it is alive, breathing, growing, enduring. A kingdom beneath the waves, built by the smallest architects of all. Chapter 12, Giants of the Sea. The ocean holds the largest animals ever to exist. Not just the largest alive today, but the largest in all of Earth's history. Larger than the dinosaurs. Larger than anything that has ever walked, flown, or swum. The blue whale is the biggest animal that has ever lived. An adult blue whale can reach 98 feet in length, longer than a Boeing 737 airplane. It can weigh up to 200 tons, as much as 33 elephants, or 2,000 adult humans. Its heart alone weighs 880 pounds, the size of a small car. Its tongue weighs as much as an elephant. A blue whale's heart beats only 2 times per minute when diving deep. Each beat pumps 220 liters, 58 gallons, of blood, enough to fill a bathtub. Blue whales are not only large, they are loud. Their calls can reach 188 decibels, louder than a jet engine, and travel across 1,000 miles of ocean. These low-frequency sounds, below the range of human hearing, allow whales to communicate across entire ocean basins. Blue whales are found in every ocean, traveling thousands of kilometers each year between feeding grounds in polar waters and breeding grounds in tropical seas. Despite their size, blue whales feed on some of the ocean's smallest creatures, krill. A blue whale can consume 4 tons, 8,000 pounds, of krill per day, roughly 40 million individual krill. They feed by lunge feeding, accelerating toward krill swarms with their mouths open, engulfing massive volumes of water. Their throat pleats expand like an accordion, allowing them to take in water equal to their own body weight. Then, they close their mouths and push the water out through baleen plates, long, fibrous filters that hang from their upper jaw like curtains. The krill are trapped against the baleen, and the whale swallows them whole. Blue whales have no teeth. They cannot chew. They swallow everything whole. Despite being the largest animals on Earth, blue whales were hunted to near extinction. In the early 1900s, 250,000 blue whales swam in the Southern Ocean alone. By the 1960s, whaling had reduced their population to just 1,000 to 2,000 individuals worldwide. Hunting blue whales was banned in 1966, and populations have slowly recovered, but only to about 10,000 to 25,000 today, a fraction of their former abundance. Fin whales are the second largest animals, reaching lengths of 89 feet and weights of 70 tons. They are the fastest of all whales, capable of swimming at speeds up to 25 miles per hour, earning them the nickname greyhounds of the sea. Humpback whales, though smaller at 52 feet, are famous for their songs. Male humpbacks sing complex songs that can last 10 to 20 minutes and repeat for hours. These songs evolve over time. Whales in the same region sing similar songs, but the melodies change each year, as if they are composing new music. Scientists believe the songs are used to attract mates, but their exact purpose remains a mystery. Humpback whales are also famous for breaching, leaping almost entirely out of the water and crashing back down in spectacular splashes. A 40-ton humpback launching itself into the air is one of nature's most impressive displays of power. Sperm whales are the largest toothed whales, and they dive deeper than any other mammal. They can reach 59 feet in length and weigh 57 tons. Sperm whales regularly dive to depths of 3,280 feet, and some dives reach 6,560 feet or more. They can hold their breath for 90 minutes while hunting in the deep. Their primary prey is giant squid, elusive creatures that live in the deep ocean and rarely come to the surface. Giant squid can grow up to 59 feet long, including their tentacles. Their eyes are the largest of any animal, 12 inches across, the size of dinner plates. These enormous eyes help them detect faint bioluminescence in the pitch-black deep. Giant squid have 8 arms and 2 longer tentacles covered with suckers lined with sharp, tooth-like rings. They use these tentacles to snatch prey from the water, pulling it toward their beak, a hard, parrot-like structure capable of cutting through flesh. Despite their size and fearsome reputation, giant squid are rarely seen. Most of what we know comes from dead specimens washed ashore or caught in fishing nets. The first video of a live giant squid in its natural habitat wasn't captured until 2012, at a depth of 2,066 feet off Japan. Even larger is the colossal squid, which can reach 46 feet and weigh 1,650 pounds, heavier than the giant squid, though not quite as long. Colossal squid live in the deep waters around Antarctica and are known to be prey for sperm whales. Scars from their sharp suckers are often found on whale skin. The whale shark is the largest fish in the ocean. Despite its name, it is a shark, not a whale, but it behaves more like a whale, filtering tiny plankton and small fish from the water. Whale sharks can grow up to 59 feet long and weigh 20 tons. Their mouths are 5 feet wide enough for a person to swim inside, though their throats are only about 10 centimeters wide, so they cannot swallow anything large. Whale sharks are gentle, slow-moving creatures, often allowing divers to swim alongside them. They can live for 70 to 100 years or more, and each whale shark has a unique pattern of white spots on its skin, like a fingerprint. Manta rays are among the largest rays, with wingspans reaching 23 feet and weights up to 2 tons. They glide gracefully through the water, flapping their wings like underwater birds. Mantas are filter feeders, swimming with their mouths open to capture plankton. They are highly intelligent, with the largest brain-to-body ratio of any fish. Mantas have been observed displaying curiosity, playfulness, and even self-awareness, recognizing themselves in mirrors, a trait shared with only a few other animals. The ocean sunfish, mola mola, is one of the strangest giants. It can weigh up to 5,000 pounds, making it the heaviest bony fish in the world. Despite its size, it looks unfinished, as if someone cut off the back half of the fish and left only the front. Ocean sunfish have no tail fin. Instead, they have a clavus, a rounded, fused structure where a tail should be. They swim by flapping their dorsal and anal fins, which gives them an awkward, flapping motion. Sunfish spend much of their time at the surface, basking in the sun, which is how they got their name. Scientists believe they do this to warm up after deep dives hunting jellyfish in cold water. The ocean is home to giants, creatures so large they defy imagination. They remind us that size is not a barrier in water, that with buoyancy to support weight, life can grow beyond the limits of land. The ocean holds room for the largest, and, in their presence, we are small, quiet, and awed. We have journeyed together through the ocean's depths, from the sunlit surface to the deepest trench, from ancient waters 4 billion years old to creatures born just yesterday, from the smallest plankton to the largest whale, from ice to fire, from silence to song. If these peaceful explorations have brought you rest, please like, subscribe, and share, so others may find their way to the ocean's calm. Now, breathe deeply. Let the waves rock you gently. Let the blue surround you. The ocean is eternal, and tonight, it holds you safe. Good night.